Imagine a computer that could take a problem requiring today's fastest supercomputers millions of years to calculate and solve it in minutes. Right now, governments and major technology firms are moving past the experimental phase, committing billions of dollars to build exactly that. They are targeting a machine capable of identifying new life-saving chemical compounds, resolving chaotic global logistics bottlenecks, and recalculating math securing digital communication. It is why the struggle to master this technology is becoming a central competition for 21st century influence. Every device you use right now processes information using bits. These enormous supercomputers operate on a strict binary system, forcing billions of tiny calculations to be registered as either a 0 or a 1. Quantum computers operate on a different physical logic. Instead of classical bits, they rely on quantum bits, or qubits. By tapping into the laws of quantum mechanics, a qubit can occupy and explore multiple states at the exact same time. You wouldn't use this hardware to browse the web or edit a spreadsheet. It is designed to navigate specific, massive datasets, calculating thousands of potential paths simultaneously to pinpoint the single optimal result. By bypassing the physical boundaries of classical computation, these systems can generate answers to problems that would otherwise crash even the most advanced conventional hardware. For major powers, this isn't a curiosity. It is a strategic asset on the scale of nuclear energy or the early space program. The immediate concern is national security. A sufficiently mature quantum computer could rapidly calculate the prime factors that secure nearly all of our modern digital communication, leaving encrypted state secrets exposed. To defend against this, intelligence agencies are racing to develop and implement quantum-resistant encryption before their adversaries can finish the hardware. The first nation to operate a stable machine at scale will effectively possess the ability to bypass the digital defenses of every rival state. The United States is attacking the problem through a decentralized network. American policy combines federal grants with advanced research from top universities and aggressive investment from private technology giants. China treats the technology as a strict national priority, dedicating heavy state funding to build centralized quantum infrastructure from the ground up. Meanwhile, the European Union is running collaborative programs across its member states, while the UK, Japan, Canada, and Australia develop their own specialized research hubs. There is no clear leader today. This is an active, volatile competition fueled by multi-billion-dollar budgets and national pride. Beyond military intelligence, the commercial rewards were tangible. A quantum system can accurately simulate complex molecular interactions, allowing pharmaceutical companies to compress decade-long drug discovery cycles into weeks. That same predictive power will allow engineers to identify superior materials for electric vehicle batteries, or let logistics companies instantly find the most efficient path for thousands of daily flight routes. Climate scientists will run highly precise simulations, while artificial intelligence models and global financial markets become far more predictable. Nations that control these breakthroughs will control the patents and supply chains for a new generation of industry, while pulling the world's leading researchers toward their own infrastructure. But despite the billions in funding, the physical hardware is still in its early stages. Qubits are incredibly fragile. To function, they must be isolated inside extreme cooling structures. Microscopic amounts of ambient heat, a slight vibration, or faint electrical noise will collapse the quantum state and ruin the calculation. Right now, researchers are stuck trying to write reliable software algorithms while simultaneously engineering advanced error correction techniques to keep the physical qubits stable. Because of these physical bottlenecks, the race is less about a single breakthrough and more about a grinding war at engineering attrition. When we look at today's early prototypes, we are actually looking at the equivalent of the very first internet servers. The hardware is clunky and heavily restricted, but it holds the massive capacity to completely reorganize how we process the world. These machines will eventually sit in remote data centers, continuously pushing the outer limits of what human beings can calculate. The countries investing today aren't just building faster calculators, they are positioning themselves to lead the next century of global development. And make no mistake, the race has already begun.